Good day. For those of you who don't know me, my name is Douglas Harder, and in this topic we're going to look at optimization. So in this topic, we're going to describe what will be covered in this next section, specifically optimization. We will give a few definitions of the various terms we will use in this topic. We will discuss constrained optimization. We will also discuss some issues that occur with optimization that are more of a problem than we would have had when we were, say, doing root finding. And then we will describe the two major topics that we will be covering in this section of the course. All right, optimization involves the process of, given a function that is real valued, f at x, find an argument x such that, for example, x sub max having the property that f at x sub max is greater than or equal to f evaluated at any other point of interest. Alternatively, finding a point x sub min such that f at x sub min is less than or equal to f evaluated at any other point of interest. Now, the first process is called maximization and the second is called minimization. Solutions to the first are known as maxima, solutions to the second are known as minima, and together these are known as the extrema of a function. Now, as maximizing a function f at x is equivalent to minimizing the function negative f at x, we are going to focus entirely on minimization processes in this section. So a global minima is a point x sub min such that f evaluated at that point is less than or equal to f at x for all other possible arguments of x. Now, this is actually a very difficult problem to solve because, well, you may have a minimum that is local to where you are, but you don't know if that is actually the actual minimum. Going back to optimization, you may have climbed up to the top of a hill, but if you don't know about the existence of Mount Everest, you don't know if you've actually climbed up to the top of the tallest hill. On the other hand, a local minima is a point x sub min such that f at that point is less than or equal to f at x for all points x sufficiently close to x sub min. So more rigorously, a point is a local minima if there exists an epsilon greater than 0 such that f at x sub min is less than or equal to f at x for all x such that the distance between x and x sub min is less than epsilon. Now, as with root finding, we will discuss two cases: optimizing a real valued function of a real variable, and this would be one-dimensional, and optimizing a real valued function of a vector variable. This would be higher dimensional. And we did both of these when we were performing root finding operations, that is, solving a system of nonlinear equations. Now, in some cases, constraints may be put on the possible solutions. So, for example, a problem may be stated as follows: minimize or maximize f at some vector valued function x subject to x satisfying a list of conditions. For example, one may ask, find an n-dimensional vector x that maximizes the inner product of some vector c and x, where c is also an n-dimensional vector, where all entries of x are greater than or equal to 0, that is, they are all non-negative, while at the same time a times x is less than or equal to some vector b. So a vector a times x is less than or equal to a vector b if each entry of a times x is less than or equal to the corresponding entry of the vector b. Now, there are excellent upper year undergraduate courses that focus specifically on covering such types of optimization. The one described above is solved using linear programming and uses techniques such as the simplex method. These techniques will not be covered in this course. Now, when you find a root, it can usually be found to significant accuracy. For example, if you were to try to find a root of sine of x, that can easily be done to 16 significant digits. This is due to the ability that we are finding a root. And so when we evaluate the function at a floating point number close to the root, the value that's returned can be as small as 10 to the negative 300. So we can actually reasonably rely on this technique. However, if we're finding an extrema through function evaluations, there may actually be very many x values that ultimately map onto the exact same floating point number. So if that's true, there's very little we can do to distinguish between the actual minima and a number that evaluates to that same floating point number. All right, so let's assume that x sub min is indeed a minima. In that case, the derivative at that point, according to a Taylor series, must be 0, and all we're left with is the concavity times x minus x min all squared. Okay, yeah, there's an order cubed error term, but let's ignore that for now. Now, if the error term in this expression is too small, then f at x will evaluate to the same value as f at x sub min. So basically, if that error term, the squared term, is less than f min times 2 to the negative 52, 52 significant digits, the machine error, then we won't be able to differentiate between them. We won't know which one is the actual min and which is close to the actual min. Okay, so if the right-hand side, or if the second term is less than or equal to the absolute value of f at that minimum times 2 to the negative 52, we can bring all the terms over to the one side, and then we can take the square root of both sides. So we can now calculate the right-hand side, and consequently, if x is any point within that distance of the minimum, it's going to evaluate to the exact same floating point number as the actual minimum. Now, for example, if we were trying to find the minimum of sine of x, any minimum, then we would have a point that would appear to be a minimum if it's anywhere within this distance of, say, for example, negative pi by 2. That's approximately 10 to the negative 8. That's not many significant digits of accuracy there, if you actually think about it. It looks like a small number, but consider this. It seems that the most we can get is 8 significant digits of accuracy when finding a maximum or minimum of sine of x, as long as we are doing function evaluations. For example, if we evaluate sine at negative pi by 2, we get the integer negative 1. That is the floating point number that represents the integer negative 1. we can calculate negative pi by 2 plus 10 to the negative 18, and that still evaluates to negative 1 exactly. Same thing with negative pi by 2 minus 10 to the negative 8. So basically, any value within 10 to the minus 8 of pi by 2 will appear to be a minimum, because sine evaluated at all of those points will be negative 1. Now, if we try to evaluate it at a slightly larger number, say negative pi by 2 minus 10 to the negative 7, now we get a value that is different from the actual minimum. Therefore, as far as the computer is concerned, sine of x has a minimum at absolutely every single value of x on this interval. And as you can see, the correct answer lies somewhere in between, but there's a good chance that you may not even get anything more than 8 significant digits of accuracy. If you get any more, it's more by luck than by design, because the computer cannot differentiate between any of those numbers, because all of those evaluate to the exact same value, the floating point number representing negative 1. However, in this section, we will be looking at unconstrained optimization, finding local minima of a real valued function of a real variable, and then we will go on to unconstrained optimization, finding local minima of a real valued function of a vector variable. Following this discussion, you now have an idea and an overview as to what will be covered in this section. You're aware of some of the ideas and definitions behind optimization, and you are aware that we will be first looking to optimize real valued functions of a real variable, and then go on to optimize real valued functions of a vector variable. And we will focus on minimization, as maximization is simply minimizing the negation of the function. You are also aware that optimization may not be as accurate as root finding, and there's no way around that limitation, because too many numbers can possibly evaluate to the same maximum or minimum value. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!